let's get started. Since we learned this one, it's been a while since we learned these things. Let's review what we discussed last time. So this is the picture of a transmitter, receiver, and we have a channel between the transmitter receiver, right? But what we are trying to look at is the channel between the transmitter receiver is unknown to us, or it can be measured, but we cannot control the channel. Okay, so channel is given to us. Typically, the channel is not perfect, right? So this channel, let's say this is a simple block. Every block has an impulse response, which means that the impulse response will characterize this block. So when you look at the impulse response of this block, we call that as a channel, but when we look at that impulse response, if this block is perfect, then we know that impulse response will look like this, right? Which means that we have no delay, time zero, meaning no delay, and we have only one impulse, which means it's perfect impulse response. However, the actual channel is not perfect. So when you look at the actual impulse response, most likely the impulse response will look like this. So we have some delta 1, delta 2, some of the delays, and we have a multiple path. We call that as a multipath. We have a multipath, and we have some of the delay. Okay, so that is most likely a practical impulse response. Impulse response of practical channels. So this is a perfect, ideal impulse response. But of course, we cannot get this, right? In the practical channels, most likely you have this kind of impulse response. We are looking at this one, right? So this channel has this impulse response. Now, when you have this impulse response here, right? We have this impulse response here. What's going to be the problem? When you have this impulse response, what that basically means is that this block has a memory. Remember that we discussed the memory in the channel or any block? How do you know? If you have only one impulse, which means it's a memoryless, we have no memory. But we have two or more, which means that we have a memory. Okay? Think about this one as a delay, right? Think about the actual memory, like a flip-flops, right? You get an input to the flip-flop, and when you get the next input, the previous input now moved to the next, it's shifted to the next flip-flop. It's like a shift register. You know shift register, right? It's like exactly like this, right? So you have one input, and the next input, when you have a second input comes in, the first input now moves to the next. And second input comes here. You get the third input. Now the first input moved to the third one. Second input moved to the next. The third input comes in here. Okay? So that's what it looks like. It's like a shift register. So what that means is every time when you have more than two paths, that means we have a memory. Every time when you have a memory here, you're going to get ISI, intersymbol interference. So the problem of this is that we have intersymbol interference. That's what's happening in hardware also, right? Think about the hardware. Let's say you have input. Think about hardware. Okay, you have a flip-flop like this, shift register. Maybe some of you are familiar with this kind of thing. Let's say this is your hardware. Let's say this is your hardware. You have an input, you have an output, right? But we have a memory. Each one is a flip-flop. Now what's going to happen? Of course, the ideal hardware, the really ideal hardware is like this. You have input, immediately you have output. Maybe you can have like, maybe you multiply 2. It's like amplify 2 times. But still, if you have this hardware, that means whatever input you have, you're going to have 2 times bigger output immediately at the same time, right? No delay, no memory. But now, let's say you have one memory here. Then what's the relationship? You have input, let's say input is xn, output is yn. Then what's the relationship? Output is always same as input, but you have one delay, right? Because of this, you have a delay. But in this case, you have a delay, but there's no ISI, no intersymbol interference, just a delay. So this one is actually same as this impulse response, right? This impulse response and this one looks the same, only delay. Of course, this value is 1, the coefficient 1. So that's what's happening. Now then, let's think about, now let's go back to this one. What about this one? In this case, initially the memory is 0, initialized to 0. Let's say your first input comes in here. Your first input, let's say x1, moves into here. And now let's say you have x1, x2, x4 comes in. When you get to x2, x1 now moves to here. x1 moves here, now you get x2. Something like this, right? Every time when you get a new sample comes in, they are moving to the right. They're shifting to the right. Now let's bring the x3. Then now x3 comes in here. x2 moves to here. x1 moves to there. Now think about it at that point, right? Now we have x3 comes in. So of course you're going to get y3. So what is y3? y3 is not same as x3 anymore. Then what is it? In this particular case, maybe you have another addition here. In this case, what's happening is x3 is actually y3 is x3 plus x2 plus x1. Right? That's what's happening. So that means it's intersymbol interference. What you want to get is you want to get y3 equal to x3. That's what you want to get. That's like this, right? You have x3 comes in, your output is y3, and y3 equals x3. That's the ideal channel or ideal hardware with memory, with no memory. But in this case, because of all this memory in the channel, now what you're going to get is your output is an addition of all these 3. What I want is this. I want this only. Okay? But because of all this memory, the previous samples remain in the memory, and now much later it will add it. It will be added all that, and that's what you're going to get here, right? Same thing happens here. Because of all this multipath, each of these works as a memory. So because of that, in this particular channel, what you're going to get is basically the same thing. It's somehow, in this case, you can say it's a C1, C2, C3. I'm talking about the amplitude, the coefficient of each one. Each one may be C1. This one, second tab is a C2. The coefficient of the third tab is C3. Okay? In that case, you're going to get this output. Let's make this delay also as a natural number like this. Then you're going to get this kind of output when you have this impulse response. So what you want to remember is when you look at this impulse response, okay, this kind of multi-path impulse response, you need to remember memory. This impulse response means exactly the same as memory. It's not actual hardware memory, but the concept is same as hardware memory. That's why we call this a memory. Okay? So this is a memory channel, and we have so many memories. In this case, we have four different memories, right? Like in this case, 3, but this impulse response means that we have 4 different memory. So every time when you have this kind of memory, your output will be like this. It's not going to be like y3 equal to x3. Instead, you're going to have each output will be addition of all these previous symbols, each with a different weight. So that's what's happening. So this is clearly a problem because we have ISI, right? Why do we have this problem? Because impulse response looks like this. But this impulse response, we cannot change it. Why? We cannot control this impulse response because this is channel, right? We didn't make this impulse response. We simply measured in the channel. So this channel is given to us. Sometimes this channel is wireless channel, sometimes underwater, sometimes cable channel. Every channel has a different characteristics, different impulse response. But whatever impulse response the channel has, it's given to us. So this is given to us. We cannot change it. So because of that, we have this ISI. Then what should we do? So because we cannot change anything here, and because of that, we have ISI problem. Now what we can do is that we design a transmitter. We design a transmitter here. Okay, we design this transmitter. We also design this receiver in order to cancel this out. That's the idea. Transmitter, at the end of transmitter, we have transmit filter. And very first, at the receiver, we have receive filter. Okay, that's our design because transmitter, receiver, we can design. Channel, we cannot design, we cannot control. But everything in the transmitter, everything in the receiver, we can do everything, right? We design the hardware. So what we can do is we design a very special hardware called the transmit filter in the transmitter side. And also we design receive filter in the receiver. And then put that together and the wrap around with the channel. And make this red block as a special block. Okay, this red block is a concept. Again, don't confuse about this red one and the channel and things like this. Actual hardware is that from here is a transmitter. This is a hardware, receiver hardware. Okay, this channel is the actual channel. What I'm saying is a red box is not the hardware, right? Red box is a conceptual box. It's just concept. Because everything is a sequential, right? You have your original information to transmit. Your information is being modulated and encoded, and eventually it'll be transmitted through the antenna. Once your information is modulated and become the symbol, and then transmit to the antenna, that goes into the channel, right? And then you receive the symbol through the antenna. You have receive antenna, right? You receive the receive symbol, and that symbol goes to the filter, and then that symbol goes into demodulator, and you eventually make a decision. So all these things is a sequential from here all the way to the right. Okay, we are going sequential like this. Everything starts from here all the way to here. Right? So it's sequential. So simply speaking, right? You have your original input, original information. That information goes to some block, and then you have output. Then what's the relationship between these things? Your output is going to be a convolution of this impulse response and your input. Same thing here again, here again, here again, right? Just think of this one is again, input is this, and you have output. This block, again, you have input and you have output. This one, again, input and output. Everything is like this, right? So in that case, actual hardware is from here to here transmitter, here to here receiver, but forget those things and make the whole picture as a block diagram and make these three block diagram as a group, right? And make this whole block as one simple block. Again, this is not a hardware block, okay? This is not a hardware block. Just to make these three blocks as one concept, one simple block. Once you do that, right? Now then, this channel has its own impulse response, but since we design a special transmit filter, receive filter, and wraparound, so that this red block can be the ideal block. That's what we want to do. So our goal is we want to make this red box to have this impulse response, because this is the ideal impulse response, right? We want to make this whole block to look like this. That's what we want. This one actually is not this. The channel actually looks like this. But when we put these special things here and then put it together, then we want to make this. Does it make sense? That's our goal. Okay, that's our goal. Okay, so here are some equations, but this equation basically simply tell you the relationship between the input and output. Each one is just convolution, right? XT is convolution of ST and HT and things like this, right? That's the simple relationship between the input and output from the previous picture. Same thing here, but what you want to remember here is that when you look at the convolution, generally, right? Convolution, based on the definition of convolution, every convolution has a summation from minus infinite to infinite. That's based on the definition of convolution. Maybe if you consider a finite samples, if you think about these two signals and you want to do convolution, then in this case, this is not summation from infinite to infinite, right? This is not like this because number of samples here and number of samples here are finite. However, think about let's say you want to do convolution of these two signals, and one signal has infinite samples. In that case, when you write this convolution in mathematics, you're going to have minus infinite to infinite, right? So the original definition of convolution is a summation from minus infinite to infinite. So in this case, we basically follow the original definition of convolution because we don't know. AK is input samples, but input sample may be infinite, so we don't know. So go back to the basic definition of convolution. So this is a convolution definition, right? So because of these, we have so many samples, but when you look at this, right, we have this one basically means that the ith output. We have so many outputs, but we have ith sample, output sample. So this is an ith output sample. I can be 1 or any value, just arbitrary value of I. So as an arbitrary value output sample, we can write it this way. Right? We can rewrite this summation into this way. So from here to here, it's basically simple. It's the same thing basically. But what we can do is we can separate the AI, because in this case, K is from minus infinite to infinite. So we have A minus infinite all the way to A infinite. So in between we have AI, right? So we can just separate AI here and the remaining summation, put it here. So in this summation, we have no I. K is not I because we separate the I here. So we want to write it this way. Instead of this, we rewrite it this way. And the reason that we want to separate the AI component is because that we are looking at the ith sample, right? So what is AI? AI is ith input sample. Ith input sample, that's AI. So when you look at simply this relationship, this, yi equals that relationship is like yi equals root square e ai. When you look at this relationship, that basically means that you have input at ith sample time, right? And your output is going to be simply a simple amplification, no delay. So what's the relationship here? That relationship is like simply like this, right? Simply like this. That's what I draw here in the previous picture, right? So that's the relationship. We have input AI comes in and simply multiply some value, some constant value, and then you're going to get output immediately. See, both one has I index, meaning that both are same time, same index, no delay. And no memory, of course, right? So that's what we want. So what we want is only this one. This is what we want. However, based on the definition of convolution, unfortunately, we have more terms, right? We are basically following the definition of convolution. The original definition of convolution, you have many terms. But we don't want this. We only want this, but we have so many terms. So now what we're going to do is that we want this only, and we don't want this, because this part is basically intersymbol interference. And this part is basically like this. And this part is basically memory. And we don't want memory. And we don't want these things. We want this only. This, right? That impulse response is same as this kind of input-output relationship. Mathematically, that basically means this. So this one, same thing. And that's what we want. But in actually, what's happening? This is what is happening. And because of that, we have these many equations. So what do we need to do then? What we need to do is, we need to remove this. Okay, we want to remove this. Now the question is, how can you remove that? That's why we want to remove these terms. That's why we need these things, these two. Transient filter, receive filter, we put those things. We put these two filters in order to remove those terms. Okay? So using these filters, transient filter, receive filter, those two things, using those three things, we want to remove these terms. Okay? So that's what we want. Okay? So once we remove these terms, we eventually make this red box to be Nyquist channel. So going back here. If we can remove these summations, right, all the other terms, now then we can convert these red box to be Nyquist channel. So Nyquist channel is the ideal channel, like this. So let's take a look at the Nyquist channel here. Nyquist channel is just channel. You have input, of course you have output. Just a channel, another channel. But this is a special channel such that this channel has impulse response like this. So that means this is the ideal channel. Also, this one has a frequency response. Something like this. So that's the characteristics of Nyquist channel. What we can notice here is that typically, right? Typically, when you have this ideal impulse response, your frequency response will be flat, right? Because these two are the Fourier transform relationship, right? Think about the Fourier transform of impulse, time domain impulse in time. When you take a Fourier transform, it's going to be flat in frequency, right? This is the relationship between these two, in general. However, when you have this kind of Fourier, the frequency response, we cannot use it because that basically means that you are going to use all the frequencies. That's impossible, right? You cannot use all the frequencies. You're going to use only your bandwidth, right? So therefore, every channel should have this kind of frequency response. Your response will be limited within your bandwidth, okay? Because other frequencies will be used by others. Other people use these frequencies, right? You're going to use only your bandwidth. But if you limit the frequency response to your own, now then the problem is that our time domain response is going to be sinc function. It's no longer ideal. You're going to have time domain sinc function, right? So this is not ideal response, impulse response. This is not ideal impulse response. Again, these two are the relationship between the frequency and time domain, right? But in Nyquist channel, what we are doing here is that we choose a very special sampling frequency. Think about the relationship between these two. This is continuous time. This relationship, again, this is continuous time. Okay, these two are the time domain, frequency domain dual relationship. Same here, right? These two are like a pair. These two are pair. These two are pair, right? But this is like a continuous time. Continuous time. When you have this kind of continuous time impulse response, but still you apply a very special sampling frequency, then you can change these things to be like ideal impulse response. Okay? That's the idea of Nyquist channel. So when you think about the Nyquist channel, the difference is that this one involves some of the sampling. This relationship is a continuous time. Okay? Continuous time, very, very ideally, this is the ideal response, impulse response. This is a frequency response, okay, in the continuous time domain. But when you think about the very specially chosen sampling frequency, then we can make this kind of impulse response and frequency response. Do you understand what I'm trying to say? Okay, what I'm trying to say is we want this impulse response. And we also want this frequency response. You cannot use all the frequency, right? You want to use this frequency response, and we want to make this impulse response. Because this impulse response means that no memory, no delay. Perfect, right? Now what's the problem? These two are not pair. This is a pair. This is a pair, right? If you have this time impulse response, you are not going to get this frequency response. You're going to get this, right? And if you want to get this frequency response, you are not going to get this time impulse response. You're going to get this instead, the blue one, right? So the problem is we want to get this in time. At the same time, we want to get this in frequency, but these two are not pair. These two are not partner. The partner of this is this guy. And also partner of this is this. These two are not partner. How can you get these two at the same time? That's what I'm trying to say. The only way is that you get this frequency response like this, then you're going to get blue time domain response, impulse response. Okay? In continuous time. Okay? In continuous time, you're going to get this blue time domain impulse response. However, since this is continuous time, what you want to do is you're going to do a sample in a very, very carefully sampling frequency such that in every zero crossing point, you have a sample. Once you do that, now then forget the continuous time. Since you do sampling, okay, look at only the samples, digital samples. When you look at only digital samples, then it looks like almost same as this. That's what we were trying to do. Okay, that's the idea. So that's the idea of Nyquist channel. You have to select a very sampling frequency very carefully in this case. So that's how you achieve the Nyquist channel. That's the idea of the whole thing. So this equation here, right? The first equation here is simply tells you what we want in time domain. So that basically means that this. Okay? Because here, I equal to 0, when I equal to 0, you have something. When I equal to 0, you have something. All the other I, you have a 0. So you have 0, 0, 0, 0, things like this, right? So this is what we want in time domain. Once you have this, right, now the Fourier transform and go to the frequency domain, you're going to get this sinc function in frequency domain. So that's all it says. It's nothing more than that, just simple equations to explain the Nyquist channel. Okay, so let's just move to the graph here. This one visualized the Nyquist channel in time domain, also in frequency domain. Again, what we want is this. We want to get this. Okay? We want to get this. So this is a Nyquist channel. Look at the frequency domain first. In frequency domain, we have this rectangular frequency response. That's this one, right? So we have this rectangular frequency response. But when you have this rectangular frequency response, we're going to take a IFFT, inverse Fourier transform, to go back to time domain. Now we have this sinc function. And we don't want to get sinc function. We want to get this. Then how do you change this sinc function into this? That's sampling. So where do you sample? This is time domain. So you sample here. And you're going to then sample here, here, here. That's where you sample it. This is time domain, so you can sample it, right? So once you do sample like this, then you're going to get this time domain response in digital domain, in the discrete time domain. Okay? So this is the value. When you have this bandwidth in frequency, you need to choose this value as your sample duration. Okay? So once you do that, now you're going to get a Nyquist channel. And what you want to remember about Nyquist channel is Nyquist channel has these impulse response and frequency response. Generally, you cannot get these two because those two are not partner, right? These two are partner, these two are partner, these are not. But that's what you want in Nyquist channel by choosing a very specially, carefully chosen sampling frequency. Okay? So that's the idea of Nyquist channel. One thing that you want to remember here is that it says optimum pulse shape. It also says optimum pulse spectrum. Okay? It's a optimum here. Optimum. And another thing that you want to remember. So every time when you see Nyquist channel, it says optimum. Optimum means what? Best. Best. Optimum means best. And also optimum means ideal. So this is like ideal pulse shape. Pulse shape. So optimum means ideal. Generally, okay? Generally, optimum means ideal. So Nyquist channel's optimum or ideal pulse shape. Another thing that you want to remember is when you look at the time domain shape, time domain pulse, you're going to see a pulse shape. This means time domain. In frequency domain, instead, you're going to see a pulse spectrum. So every time when you look at the spectrum, that means frequency, right? Spectrum means frequency. Every time. Everywhere, when you hear the spectrum, that means frequency. In this case, when you see the pulse shape, that means time domain signal. Okay, time domain. So this is the optimum or ideal time domain pulse shape of Nyquist channel. This one shows you the optimum or ideal pulse spectrum. So this is what we want. Now what's the problem? The problem is Nyquist channel is perfect or ideal. That means we cannot, unfortunately, we cannot implement this. In practical system, we cannot make this. This is just ideal. Okay? We cannot make this. Why we cannot make this? The problem is that look at the time domain, pulse shape. We have sampling, we do sampling every 1/2 B0 time, but we need to do also sampling the negative time. What does it mean by negative time in impulse response? Okay, so that's something different. Let's say this is ideal impulse response, right? Let's say I have impulse response 1. What does that mean? That means we have delay 1, right? We have delay 1, which means you have some input, we have 1 delay, you have output. This is memory, okay? So this one basically same thing. This is just hardware block, this is just impulse response picture, but these two are same thing, right? We have a delay 1. This one has a flip-flop with a delay 1. Let's say delta. Delta is a delay. Now what is this one? Let's say you have a -1 in the delay. What does that mean? Okay, so let's go back to 1. So 1, what that means is you have y and x n. So y n equals x n plus 1. So we have 1 delay. No problem, right? So in the practical system, of course, there is a delay, processing delay. So this one perfectly makes sense to us. What is this one? That means we have a delay of -1. What does that mean? That basically means it's like this. It's like this, right? So what does that mean? That basically means, think about n equal to 2. Then what does it mean is, that's what they mean. What does it mean? No, actually, okay. I think I got it wrong. So when you have a 1 here, this is the 1, right? Yeah, I put it wrong. So this is when you have a delay 1. So what I'm trying to say is, when you have a -1 delay, you're going to have this. So what that means is your, let's say 2 equals x3. So that's the case of -1 delay. So what does that mean? Your output at the second sample is going to be your input to the third sample. So this is a sample in the future. So how can you get the sample? How can you get the output for the future sample? This is impossible, right? This is non-causal system. You heard about causal, non-causal, right? This is causal because whatever happens in the past will impact the future. That's natural. But your future sample cannot impact the past. That's like a back to the future thing, right? So this one does not make sense in practice. This is non-causal system. When you come back here, we have non-causal samples here. So these things, of course, you cannot, practically, you cannot make this because non-causal. So this Nyquist channel is perfect and ideal or optimum pulse shape. The problem is this is non-causal. So in practical system, you cannot make it. Then what do you need to do? So going back all the way, so we started from here, right? Okay, summarizing all these things, our problem started from the channel. Okay, all the problems always start from the channel. Our channel is a bad channel, so we have, in the channel, we have a lot of memories. We have, because of all this memory and multipath, we have ISI, right? So this is a very bad thing. That's our starting point. So because of that, because this guy has a lot of memory and ISI, what we are trying to do is we are going to design a special filters and put that all together, and we want to make this red one to be Nyquist channel. That's what we want. Okay, so that's why we have a goal like this, and we finally learned how to do that, how to do these things. But the problem is, this one we cannot make it. Then how can you do it? What we can do is that we cannot make a perfect channel, perfect filter like a Nyquist channel, but instead at least we can try. We can do our best. So one of them is pulse shaping filter. So this is a practical design of the filter. It says a pulse shaping filter, right? What filter are we talking about? We are talking about this filter, okay? Ideally speaking, we want to make these two filters in order to make Nyquist channel. But the problem is we cannot make it in practice. So that's why we are trying to design these two filters. Not ideal, but we can try our best. So that's a pulse shaping filter. So when you look at this pulse shaping filter, is it frequency domain or time domain? This is time domain, right? I told you in the previous picture. Every time when you look at the pulse shape, that means time domain. In frequency domain, you'll see pulse spectrum. Okay? So the pulse shaping filter, this is the time domain filter. Okay? So what is the purpose of this pulse shaping filter? The main reason we want to get this pulse shaping filter is this one and this one. Okay? First reason, inter-symbol interference or ISI is reduced to 0. We want to make no ISI. How do you do that? When you get this, that means no ISI because there's no memory, no multipath, right? So the first reason basically means that we want to make impulse response to look like this. Okay? This is what we want. That's what this means. What is the second reason? Transmission bandwidth is conserved. That basically means we want this. Our transmission bandwidth is conserved into our bandwidth. You cannot use all the frequency, right? Your bandwidth is limited. That's what we want. So we have two different goals. Okay? We want to, this is a design parameter, design requirement. And these things is same as this. So in order to get these two, and also we have to think about the physical realizability. That means your filters should be causal. Okay. The Nyquist channel has these two impulse response and frequency response, but the one thing that is missing in the Nyquist channel is you cannot realize in the filter in practical systems. So in this pulse shaping filter, what we want to do is we want to get these two. At the same time, we want to make it in practical system. We also want to get the physical realizability. Okay. So we have some equation here, but let me go to a next picture. Let me skip this equation here and go all the way to the equation first, the graph first. It's easier to look at this and then look at the equation. So simply speaking, this is one of the best example of pulse shaping filter. And this filter called raised cosine pulse shaping filter. Raised cosine. This is the name of the filter, raised cosine. Raised cosine. Why do you call this a raised cosine? Cosine, think about only one period of cosine. One period of cosine looks like this, right? This is one period cosine. Let's flip this. When you flip this, looks like this, right? This is just cosine, but I just flipped it like a minus cosine. And then let's raise it up here. Then it looks like this. That's what you have here. Okay? So it's like a raised, it is cosine, but it's a raised cosine. Okay? Just follow the what it looks like. So that's why it's a raised cosine filter. This one is a frequency domain response. This is a time domain response of the filter. And what I want to tell you is that it's a comparison between this raised cosine pulse shaping filter with the Nyquist channel. Because Nyquist channel, we know that it's ideal pulse shaping filter, right? In the previous Nyquist channel pulse shaping filter or ideal pulse shaping filter look like this in frequency domain, rectangular in frequency domain, and sinc function in time domain. Okay, so let's go back to that picture. Let me go back. This was a Nyquist channel, right? Nyquist channel has a rectangular frequency response and perfectly sinc function of time domain response, right? That was the case of Nyquist channel. Now the problem is that we cannot make that in practical system. So that's why we have to redesign it. This pulse shaping or raised cosine pulse shaping filter does not have a rectangular in frequency. Okay? That's the difference. Nyquist channel has a rectangular pulse in frequency, but this raised cosine does not have a rectangular. Instead, this one has like a little bit slowly going up and flat, slowly going down. Or you can make slower like that and going like that. So you can control it. This filter, we have a parameter called alpha. Okay? If you change the alpha value, you can make it as a red or you can make it as a blue. The red is the case of alpha equal to 1 and blue is the case of alpha equal to 1 over 2. Okay? So by changing the alpha, you can make it as a blue filter or you can make it as a red filter. You can control it. You can design it different way. But anyway, we are not going to get rectangular in frequency domain. Instead, you're going to have a little bit round. We call this a roll-off, right? We have a little bit roll-off, left and right. Once you have this, we have a little bit of problem. What's the problem? Compared to the Nyquist channel, this raised cosine has a little bit of problem. The problem is the Nyquist channel has the rectangular pulse, so you're going to need only this spectrum, this bandwidth. But this raised cosine, you need a little bit more bandwidth, right? You have a little bit more bandwidth. That's one problem. But anyway, that's what it looks like. Let's look at the time domain. In Nyquist channel, your time domain pulse was perfect sinc function. Okay? Because we have a rectangular in frequency, you have a perfect sinc in time. However, in raised cosine pulse shaping filter, let's think about alpha equal to 1 over 2. In this case, the frequency domain, you have a little bit of slowly going up, slowly going down. So when you go to the time domain pulse, that will look like this. Look like this. It's not sync. This one is a sync. This one is a sync, right? But it's not exactly sync. So this red one and this red one is a pair. What about alpha equal to 1? When you have alpha equal to 1, now then the time domain signal looks like this. So this red one and this red one are pair. Time domain, frequency domain. So this is a shaping of the pulse. Okay, so that's the pair. One thing that this does not tell you. So typically when you look at the textbook, right, then this is the end of the story in your book. But we do not completely understand what that means, right? So, okay, let me tell you some more things. Okay, here's the simple thing. This is a filter, simply. Okay, think about simple way. This is a pulse shape filter. This is filter, just filter, right? Think about just regular filter. Every filter you have an input and you have an output. And this filter has this impulse response in time and this frequency response in frequency. Okay? Now let's say this particular pulse shape filter has this, let's think about the red one here, red. Okay? I'll choose the alpha equal to 1. So we're going to have this red frequency response here and also red time domain response here. Now what's going to be the input? Our input is like digital samples, like 1, 0, 0, 1, something like this, right? So that means in time domain, let's say 1 means this, 0 means this, another 0, another 1. This kind of signal comes into the filter. Okay? That signal comes into the filter. Now then, what is the output? That's what we have here. Okay, let me simply think about this. Forget all these things. Let's go back to the basic and think about this. Whatever happens inside the filter is just regular convolution, right? Now we have this signal. You do convolution with this. Maybe too big. What's going to be the output? Just do convolution. It's not multiplication, right? It's convolution. So once you do convolution, what's going to be the output? Your output is going to be, this is a simple rectangular pulse that is convoluted with some kind of Gaussian kind of curve. Then your output is going to be like this. Okay, so this pulse comes in here, and that pulse also goes in here. So that's your output. Okay, what does that mean? That basically means is that you have a filter called a pulse-shaped filter, and this pulse-shaped filter has this impulse response. And what's your input? Your input is rectangular pulse. Then what is your output? That output looks like this. So why do you call this one as a pulse-shaped filter? That's because that original input, your original input sequence, looks like rectangular. Rectangular is your input. In practical systems, you cannot transmit rectangular signal. You can never transmit rectangular signal. Why is that? If you transmit a rectangular signal, that means you are using all the frequencies, right? So rectangular pulse means it has an infinite frequency component, right? Because when you convert this one in frequency domain you have sync function. So you are using all the frequencies. So definitely you cannot do that. What you want to do is your bandwidth has to be limited. So that's why you cannot transmit this in practical systems. So what you need to do is you have to do shaping. This is a shaping. Like this rectangular impulse, rectangular signal, you just like cut here. Like make it smooth, like a shape. Okay, like a shape. So this is the output. Your spectrum, your time domain pulse will be like round here, a little bit around here. That's a shape. So that's why we call this a pulse shape. Okay, make it smooth, round. Okay, that's what is happening. But how do you do that? This pulse shape filter should have this kind of impulse response. Then you're going to get this shaped pulse, and that is the time domain impulse response. So once you have this kind of impulse response, now you get this signal goes into the filter. What is going to be the output? This rectangular kind of input signal will be rounded. So it's like this. This is going to be your output after the pulse shape filter. So that's what we want. And once you do that, your signal is limited into these two frequencies. Okay? In earlier previous one, you are using all the frequencies, but since you have done pulse shape filter, your frequency component will be limited into your bandwidth. And in time domain, it looks like round based on the pulse shaping. That's the main purpose of pulse shaping filter. Every transmitter will have this. By the way, this is the transmit side. Okay? Transmit side, typically. Okay, so let's go to think about this one a little bit more. So there is a concept called the I pattern. Okay? What that basically means is that you transmit this shaped pulse, right? You transmit this kind of pulse. Now then this kind of pulse go to the channel. And in the channel, always your transmit signal will be reduced. And also there's some noise and interference and everything comes into the channel. So because of that, when you receive it, you're not going to receive this signal. This is what you transmit. You're not going to receive this, right? You receive something different. Now at the receiver, we are going to measure the eye pattern. This is at the receiver. And the reason that we call that as eye pattern is like this. So this, let's say, look at this picture. This is what we transmit. Okay, this is our transmitted signal. And why the transmitted signal looks like round? Because of pulse shaping filter. Okay? Because we apply the pulse shaping filter, transmitted signal is not going to be rectangular. Your signal is like a round. And you receive these things. And at the receiver, what we are going to do is that at every sample time, we just put this one, the first sample duration, and draw it here. And then the second sample overlap onto the first. Third sample overlap again. So like a first sample, second sample, third sample, every sample signal, we bring it and put it all together, overlap, again, again, again. Once you do that, right, this first one, draw like this. Second one, come here. Third one here. Fourth one here. And you keep doing it. Every sample you draw it. Then you're going to get this, 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 this. You keep drawing. Like, think about the 1,000 samples. You keep drawing it like 1,000 times, right? Put it again, 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 again. That's called the eye diagram. And why do you want to do this? The reason is, if the timing and noise and interference, that is pretty good, that means when you draw overlap again, 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 your eye, this looks like an eye, right? Human eye. This eye will be open. That means open. If the channel is very bad, or your timing has some problem, now then, since you draw it overlap again, 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 if the timing is a little bit off, then your drawing comes like this. Like this. In that case, it's like the eye is closed. So by looking at the eye, sometimes you see the eye is open or eye is closed. By looking at that, now you can measure a lot of things. Timing issue, on some noise issue, interference issue, all these things. So that's why we draw the eye diagram. So every time in your overlap and draw in again and again, you're going to see these kind of things. Okay? So here's an example here. So look at these two. This picture actually shows you a pretty good eye. The eye is pretty open. Okay? Maybe this one is the case of 1,000 samples, things like this. That looks like a pretty good eye. Think about this one on the next slide. This one, compared to the first one, compared to the previous one, this one is a little bit closed. But this is actually still okay. But when you compare this picture with the previous picture, this is much cleaner, right? This is a little bit dirty. And the reason of that is we have some of the noise, some of the timing issues, and things like this. So we can actually measure those things based on this eye diagram. That's the purpose of this. Okay, and the channel equalization we can talk about it next time.